Here we'll take a look at how to handle a variable force when your force is a function of time, when it's a function of position, and when it's a function of velocity. And then we'll zero in on this third case and talk about drag forces. So, okay, three cases here. First case, what if your force is a function of time? Then your best asset is Newton's second law. In this form, indicating that the rate of change of an object's momentum is equal to the net force on the object. It's a vector equation, so really we could represent it as three separate equations, one for the x component, one for the y component, one for the z component. You can see I'm sort of turning this derivative into an integral here. Let's pick out just the first equation here, just the x direction, integrate both sides, and that gets us here. So if our force is a function of time, we're likely going to want to integrate that function to find the impulse exerted by that force. This integral here will give us the change in momentum for that particle. So this is a reminder to us that a force acting over time transfers momentum. So okay, this is final momentum minus initial momentum on the left. So your delta P here equal to this integral, which we call the impulse. Here's an example. Suppose your force is a function of time. Suppose it's this function of time. It's this quadratic function of time where b is some constant here. Okay, so we're going to put this into Newton's second law. So integral of dp equals our force integrated against dt. So let's say we start from time 0 to go to time t. We start with some initial x momentum. We're going to some final x momentum. Find our antiderivative here, and that gets us to this. We have the momentum as a function of time. And we could just divide that whole thing through by mass to get your velocity as a function of time and find it's this cubic function. So that's generally what you would do. If you have a force as a function of time, you're going to want to integrate it, use N2L to get the momentum or the velocity as a function of time. Case number 2. What if your force is a function of position? That's a very special kind of force. We call that a conservative force. If your force depends on position only, then there will exist a corresponding potential energy. So the work done by that conservative force, given by this work integral, in general, if we're moving in 3D, then we could represent this integral with our dot product here, f dot dr, as the sum of three separate integrals, the fx dx, fy dy, and fz dz integral, over some path. These would be path integrals here as you go from some initial location to some final location along a path. And that whole integral is equal to, this whole work here is equal to the opposite of the change in the corresponding potential energy, reminding us that a force acting over a distance transfers energy. So here, force acting over time transfers momentum. Here, force acting over distance transfers energy. Moreover, if the net force acting on an object is a function of position only, then the net work is given by the sum of those three integrals. And by our work energy theorem, that would be equal to delta K. So we can set this integral here equal to the final kinetic energy minus initial kinetic energy. Basically, if your force is a function of position, you're going to be using energy techniques to analyze the motion. Conservation of energy and the work energy theorem. What you're probably going to want to find is that corresponding potential energy function here. You're going to want to integrate your force over a path to find this u function. Here's an example. In our first example, we had a force that was a function of time. Let's take that same quadratic equation here, but just replace time with position. So here's our second case, a force that's a function of position only. This will be a conservative force. And so we can integrate that force against x. So here we have no y or z components. So cutting those out, we have just this x component integral equals the opposite of delta u. So here's our force integrated against x. So our quadratic function becomes this cubic function here. And since this difference is equal to the opposite of delta u, we can conclude that our potential energy, or the potential energy function that corresponds to this conservative force, would be this cubic function here. Pay attention to the signs to make sure our signs work out. And you can always check that answer. Once you've integrated your force function to find the potential energy function, you can always take the opposite of the derivative of that potential energy function to make sure you recover your original conservative force. So if you're given a force that's a function of position, basically you want to find that corresponding potential energy and then use conservation of energy equations. Third case, what if your force is given as a function of velocity? So this would be like our drag force scenario where you're moving through air or some other fluid and you have a drag force on you that tends to be stronger the faster you're moving. So a force that depends on how fast you're going. What to do if you're given a force like that? Here again, we'll use Newton's second law, although I've moved m from here to here, so instead of talking in terms of momentum here, I'll be talking in terms of velocity. It's a vector equation, so it can be represented as these three separate equations, one for each component. Let's focus in on just one component here, the x component. And now here's the key move. If your net force is a function of velocity only, then we're going to take the velocity dependence here and divide both sides through by it to move that velocity dependence down there under the dvx. So I've multiplied both sides by dt, moved dt up there, and the force are going to move down here. That gets us to this. So we have dvx over, here's all the velocity dependence here in our force function, and then dt we've moved up here, and we just have the integral of dt over m, so we get just t over m. So the right-hand side's taken care of. What we need to do is integrate dvx over this function of vx, whatever we're given here, from our initial vx to our final vx. Here is an example. We use that same example function, this quadratic function here, except this time, instead of being time squared or x squared, it'll be vx squared. B again is just some constant. It'll be a different constant from the other two examples. But here we've got a force that depends on the velocity. The force has this quadratic dependence on velocity. So we would go to Newton's second law. Here is our force function, this quadratic function of v. We're just going to bring that vx squared down here. And now the right-hand side is just the b over 2m integrated against t, so that just becomes bt over 2m. And the left-hand side, we have dvx over vx squared. So we can do this integral. Find your antiderivative. That gives us this. And do some algebra to rearrange to get something like this. So if you've got the force as a function of velocity, you're going to be integrating to get that velocity as a function of time. And the key will be to move the velocity dependence from here down under there. Move that velocity dependence from here to there, and then do this velocity integral on the left-hand side.